Chapter 1.6 is going to be transformations of functions. So before we get into graphing these functions, we just have to go over some of these commonly used parent functions. So they're either called basic functions or parent functions. So here are the main several that we'll be using. So the first one, top left, being the constant function. So a constant function is just f of x equals a number. It's a horizontal line. So that one's pretty easy. The identity function is f of x equals x. So that's going to be linear with a slope of 1, y-intercept of 0. And the next couple ones are the ones that we'll be using mostly in this section. The absolute value function. So the absolute value function is going to be f of x equals the absolute value of x. So if you plugged in numbers for x and got out its corresponding y-coordinate, you can plot the points, and you would see that it looks kind of like a V. You have the domain and a range below it, and the intervals for decreasing and increasing. And the quadratic function, bottom left here, the quadratic function is f of x equals x squared. So it is a parabola. And we can see the domain and range below it, as well as when it's decreasing and increasing. And then we have the square root function, f of x equals the square root of x. The cubic function, f of x equals x cubed, and the cube root function, f of x equals the cube root of x. So we should definitely be kind of have these graphs, be able to do like a quick sketch of them as soon as we see what function we're dealing with, because we're going to be graphing them based on these graphs. Okay, so we're going to be doing transformations to these graphs, and the types of transformations we'll be doing are going to be vertical shift, which is just moving the graph up or down, horizontal shift, moving it to the left or to the right, a reflection, it's going to be reflection over the x-axis or reflection over the y-axis, a vertical stretch or shrink, and a horizontal stretch or shrink. So let's start with the vertical shift because it's usually thought to be the easiest. So if f of x is a function and c is a positive number here, if we have y equals f of x plus c, that's going to be the graph of f of x shifted up c units. So if we're adding some c value, some number after the fact, that's going to be moving f of x up c units. And if we are subtracting c, it's going to be moving it down c units. That's taking all of the y values and adding c, meaning it would be going up c units, or if it's taking the y values and subtracting c, which moves it down c units. So you can see in this little graph kind of how this works. The one on the left, we have f of x right here. If we add c to it, it pushes it up c units, so every single point gets moved up. And then on this one on the right, we have y equals f of x. If we subtract c, then we're just moving it down c units. So let's see an example here. So let's graph f of x equals x squared, and then we'll graph g of x, which is x squared plus 2, and h of x, which is x squared minus 2. So f of x equals x squared. Before I graph that, I'm going to come up with a little table of values so we can plot some points. So the values I'm going to use for x squared are going to be the x values of -3, -2, -1, 0, 1, 2, and 3. So I'm going to plug all of those values individually into f of x and find its corresponding function value, which is the y value. So f of -3 is -3 squared, which is 9. F of -2, -2 squared is 4, -1 squared, 1. And I'm just going to fill these out quickly, double check these if you want. So these are our xy coordinates here. So the first one is -3, 9. So that's going to be right up here. Next one, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. It's going to look like this. So this will be f of x equals x squared. So anytime we're dealing with a function where it's quadratic like this should be the first thing that comes to your mind. You should be able to plot this pretty quickly. So let's graph g of x. G of x is x squared plus 2. So for g of x here, this is going to be, the plus 2 is a vertical shift up 2 units. So you can see that it's completely after everything. It's just plus 2 after the x squared. So we're going to take every coordinate and move it up 2 units. So I'm not going to move the leftmost and rightmost coordinate up because they're going to be off the graph. So I'm moving everything up 2 units. So the shape is going to stay exactly the same. And I'll connect those. And it's going to look something like that for g of x. So next for h of x, we can see the minus 2. So that means it's going to be a vertical shift down 2 units from f of x. So we're going to go to every coordinate on f of x and move them all vertically down 2 units. And we're going to connect those. And we will get that for h of x. Okay, so let's do one more here. So for f of x equals the absolute value of x. Once again, I'm just going to make a table. And in my opinion, these are the values that should come to your head when you're trying to graph the absolute value of x right away. So I'm going to plot -3 to 3 for the x values. So plugging those in, the absolute value of -3 is 3. The absolute value of -2 is 2. Absolute value of -1 is 1. And I'll just fill out the rest of these out real quick. So those are the corresponding y values. So now we have an xy coordinate. So plotting these points, we're going to get these points right here. And then connecting those with a straight line. And we get that. So remember that the sharp turning point here for the absolute value is called a cusp. Up here for the quadratic, it's called a vertex. So a turning point for a parabola is a vertex. A sharp corner, a sharp turning point is called a cusp. Okay, for g of x here, we have this graph moving down 4 because it's the absolute value of x minus 4. So we're going to take every point and move it down 4 and then connect those lines. And we'll end up with that graph. And then for the next one, for h of x, we have the absolute value of x plus 4. So since it's plus 4, moving everything up 4 units. And we'll plot those. And we will end up with that for h of x. It is the function of f of x moved up 4 units. Okay, so that is the vertical shift. So next for the horizontal shift. So once again, let's say that f of x is a function and c is a positive number. This time, when things are done with the horizontal shift, they're done on the x value, which should make sense because the x values is the horizontal axis. When things are done to the y values or the function values, they're done to the y values, which is done vertically, which should make sense because it's the y-axis is the vertical axis. So for this one, if we have f of x plus c, so notice that this time the plus c is on the x. It's directly with the x. This is going to move it to the left c units. So it's opposite of what you would think. Plus c here is moving it to the left. If we have f of x minus c, that's going to move it to the right c units. So you can see in this graph right here, if we're starting with on the left f of x, and then we transform it to f of x plus c, that moves it to the left. So the shape stays the same, every point gets moved to the left. And then the graph on the right, we start with f of x, and then we plot f of x minus c, that moves it to the right c units. Okay, let's see an example. So we're going to graph f of x, which is x squared, g of x, which is x minus 3 squared, and h of x, which is x plus 3 squared. So starting with x squared, so once again, we know this is a parabola, and I'm going to plot those points that I had plotted previously. So if you have to plug in values for x squared, go for it. You should use these points. So we get that basic parabola function. So next for g of x, x minus 3 squared, Since it's negative 3x minus 3, that means we're moving it to the right 3 units. So we're moving f of x to the right. And we knew it was a horizontal shift because it's directly on the x value, on the x variable. So we're going to move everything to the right 3 units on this graph. So every single point moves to the right 3. And we'll end up with something like that. And then next for h of x, x plus 3 squared. Once again, it's on the x value, so we know it's going to be a horizontal shift. It's plus 3, so that means it is to the left 3 units. So starting with f of x, moving it to the left 3. So every single coordinate, or every single point that we plotted gets moved to the left 3 units. And we will end up with that green curve on the left. So a lot of overlapping here, but hopefully the colors help a little bit. Okay, so that is for that example. So let's do one more with the horizontal shift. So let's do f of x equals the square root of x. G of x is the square root of x plus 5, and h of x is the square root of x minus 5. So starting with the square root of x, so since I didn't make a table for this one yet for the values I use, I'm going to make a table. So for the x values that I use, I like to use 0, 1, 4, and 9. The reason is for the absolute value, or sorry, for the square root of x, we can't plug in any negative values. And the reason why I pick these other numbers is because they're perfect squares. So the square root of 0 is 0, the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So now those are xy coordinates, so we can plot those 0, 0, 1, 1, 4, 2, and 9, 3. So it'll look something like that. So essentially half of a parabola on its side. So let's take a look at g of x, the square root of x plus 5. So since we know that it's going to be a horizontal shift because it's directly on the x. The plus 5 means it's to the left 5. So we're going to move every point to the left 5 units. And we'll get that blue curve on the left. And then the square root of x minus 5, it's minus 5, so it's to the right 5 units. So moving f of x coordinates to the right 5 units. I'm not going to be able to fit every coordinate on here. And it looks something like that. Okay, so let's make these questions, let's add a little bit to this question. Let's find the domain of each function. So let's find the domain of, let's take a look at f of x first. So for the domain of f of x, that was our original. So we can see by looking at this, so domain is the set of x values where the function exists. It's going to be from 0 to infinity. So the 0 actually gets a bracket because we're allowed to plug in 0. We're including the endpoint. So 0 to infinity, and that's using interval notation. So let's take a look at the domain of g of x. Domain of g of x. G of x is the blue one that got shifted to the left. So that got shifted to the left, so we can see that the x values that for this function that exists are going to be from -5 to infinity. So it's going to be from -5 to infinity. Once again, it gets a bracket on the -5 because we can include that point. And lastly, for the domain of h of x, so that got shifted to the right 5 units. That's the one on the right. So that domain is going to be from 5 to infinity. Okay, so now let's combine these two ideas. So we want to graph f of x, which is x plus 1 squared minus 3. So what we're going to want to do for these is, and what I will be doing for all of these, is we first have to identify what type of function we're working with, which I'll just be referring to as the basic function, which are going to be all of those functions on the first page. So we have this squared up here. So that means the basic function at the most basic level is y equals x squared. So we're going to start with the basic function and then apply the transformations. Okay, so for taking a look at these transformations, we have a vertical shift and a horizontal shift. The vertical shift is going to be the -3 at the end. So that's going to be down 3. And then there's going to be a horizontal shift. And the horizontal shift is on the x value, so it's going to be that +1. But that means it's to the left because it's positive. So what we're going to do is we're going to graph the basic function first. So y equals x squared, so hopefully we know to what points we're plotting for this. It's going to be these points. So this is y equals x squared for like the third time. So let's graph this f of x, this function, without in one step here. So it's going to be a vertical shift down 3 units. So we're going to move every point down 3, and it was a horizontal shift to the left 1 unit. So we're going to move everything down 3 to the left 1. So all of those points down 3 to the left 1. And we should end up with this. So the blue one will be our function f of x. So everything went down 3 to the left 1. Okay, so far we did vertical shifts and horizontal shifts. So for the next thing is reflection. So we have a few more things to get through. So for reflection, there's two types of reflections. It's either going to be a reflection across the x-axis or across the y-axis. So for the first one, for reflection over the x-axis, if we have a negative multiplying out front of the function, so negative f of x, that means it's going to be reflecting the function across the x-axis. Because if we're negating the y values, that means it's going to be moving across the x-axis. So what you can say is negate the y values, it flips across the x-axis. So negate the y values, reflect across x-axis. So let's do this example. G of x is negative x squared. So once again, let's identify the basic function. Let's get into a habit of doing that and writing it down. So this is a squaring function. There's a squared here. So that means the basic function is just going to be y equals x squared. So I'll graph that in a second. So let's see what kind of transformation is being done to g of x here. So to make this a little bit more obvious, we could rewrite g of x as negative and then x squared. So that means the same exact thing. So what that negative means now, it's negative of x squared. So that's going to be a reflection of y equals x squared across the x-axis. So let's graph y equals x squared. So hopefully, once again, you're comfortable graphing this. So that's y equals x squared. And now we're going to graph g of x. So we're going to essentially take those coordinates, take those points, and negate the y values. So instead of -3, 9, it's going to be -3, -9. Instead of -2, 4, -2, -4. And then -1, -1 stays at the origin. 1, -1, 2, -4, and 3, -9. So we took all of those y values and negated them, and we got g of x, which is negative x squared. Okay, for the next thing, so that was a reflection over the x-axis. For a reflection over the y-axis, this time if we negate the x values, so if x is negative, it's going to be the graph of f of x reflected across the y-axis. So for this one, you can say if you're negating the x, you flip it across the y-axis. So for example, let's graph f of x equals the square root of negative x. So once again, let's identify the basic function. So there's a square root here, so that means our basic function is just going to be the square root of x. And once again, it's always going to be something from that first page for us right now. Okay, so what we can take a look at here for f of x when we're graphing f of x is that the x is getting negated. So that negative x means it's going to be the reflection of square root of x over the y-axis. So I'm going to graph the square root of x here. So the square root of x, I used these points here a little while ago. And we got that graph. So if we're reflecting it over the y-axis, that means we're negating the x values. So the origin stays at the origin. This value comes here. This value goes over here. And this value goes all the way over here. So we get that blue curve for f of x, which was the square root of negative x. So we just negated all of the x coordinates for y equals the square root of x. All right, so for the last two things here, so far we did vertical shift, horizontal shift, and the reflections. For the next thing, we have the vertical stretch and shrink. So if f of x is our function, c is a positive number. As with every other thing, there's two cases that it gets broken down to. If c is a number greater than 1, then c times f of x is going to be the graph of f of x vertically stretched by a factor of c. So if c is greater than 1, it's going to be vertically stretched. So for horizontal and vertical shifts, we were adding or subtracting a number. For vertical and horizontal stretching and shrinking, we're multiplying or dividing a number. So this time we're multiplying c out front, which means it's vertically stretched, which means the curve moves away from the x-axis because the values are getting bigger because c is greater than 1. Okay, and now if c is between 0 and 1, and then you multiply that c times your function values, that means it's going to be vertically shrunk by a factor of c, which means the curve moves towards the x-axis. Because if it's between 0 and 1, the number is small. So we're going to be multiplying a small number by our y values, meaning our y values are going to be getting smaller, so they're moving closer to the x-axis. Okay, so if we're graphing these, to graph the function c times f of x using our basic function, what we're going to do is we're going to multiply each y coordinate by c from f of x and keep the x coordinates the same. So you can see in this little graph how this happens. So in the one on the left, we have y equals f of x. If we multiply by c out front, where c is greater than 1, we can see how it gets vertically stretched away from the x-axis. And on the right, vertical shrink, here's y equals f of x. If we multiply those f of x by a number between 0 and 1, it gets shrunk towards the x-axis. Okay, so let's do an example. Let's use f of x equals x squared to graph g of x, which is 1/2 x squared, and h of x, which is 3 times x squared. So graphing the basic function x squared here, because that's what we're using to help us graph, plotting the points, and we get that graph as usual. So let's take a look at g of x. So g of x is 1/2 x squared. That 1/2 out front is between 0 and 1. That means this is a vertical shrink. So that means the graph of f of x, all of the y values are going to get multiplied by 1/2, meaning it's going to get closer to the x-axis. So we're going to go to all of the y values. The first one has a y value of, so I'm looking at this one over here on the left first. So the x values stay the same and the y values get cut in half. So that was a y value of 9. 9 times 1/2 is 4.5. So that'll put us about right here. Next, it was a y value of 4. So that gives us a y value of 2. A y value of 1 gives us a y value of 1/2. Stays at the origin. And then it's symmetric, so same thing on the right side. So that blue curve is 1/2 x squared. You can see how it gets closer to the x-axis. So next let's do h of x. So h of x is going to be 3x squared. The 3 value out front is greater than 1. That means it's going to be a vertical stretch. So that means it's going to move farther away from the x-axis. So we're going to multiply each y coordinate by 3. So I can't really multiply, I can't really multiply the 9s, the y from f of x by 3 because that'll give us 27. So I'm going to start with the 4. 4 times 3 is 12, so I'm putting that kind of all the way up here. Next, there was a y value of 1. Multiply that by 3, we get 3. Origin stays at the origin, and then it's symmetric, so these values end up being the same. So it kind of gets a little bit out of control here. But it's going to look something like that green curve in the middle. So it got stretched vertically, meaning each point that we plotted moves away from the x-axis. Okay, so a vertical stretch or shrink, you just multiply the y coordinate by that vertical stretch or shrink, and then keep the x coordinate the same. Okay, for the last thing here, and then we'll put them all together, is the horizontal stretch or shrink. So a horizontal stretch or shrink is going to be, we have two cases again. If c is greater than 1, now we're going to have a number c multiplying the x. So once again, anything horizontal is being done on the x, so it's going to be f of c times x. It's going to be the graph of f of x horizontally shrunk. So when it's horizontally shrunk, it gets pushed in horizontally. That means it moves it towards the y-axis. So it's always opposite what you think with horizontal. For vertical, when c was greater than 1, it was a vertical stretch. When c is greater than 1 with the horizontal stretch or shrink, it's a horizontal shrink. And then when c is between 0 and 1, f of c of x is going to be the graph of f of x horizontally stretched. Horizontally stretched means it's moving away from the y-axis. So the way that we do this is if we're graphing f of cx, f of c times x, using f of x, we're going to divide each x coordinate by c from the original f of x and keep the y coordinates the same. So vertical stretching and shrinking, we multiplied the y coordinates by c. Horizontal stretching or shrinking, we divide the x coordinates by c. We can see in this graph how it works. This is y equals f of x on the left. It's a horizontal shrink. When we graph f of cx, it gets squished in towards the y-axis. The graph on the right, horizontal stretch. When we graph f of cx, it stretches it away from the y-axis. So let's see an example of this, and then we'll get into a little bit harder ones. So we want to graph f of 2x given that graph of f of x on the left. So f of 2x, based on what we have written on this page, we know that this is going to be a horizontal shrink because the c value here is 2, which is greater than 1, which means we divide every x coordinate from f of x by 2. Okay, so starting with the leftmost coordinates here, we have -4, 0 all the way over here. Dividing the x coordinate by 2 gives us -2, 0. So we plot that point. Next, we have this coordinate -2, 4. So dividing the x coordinate by 2 once again, negative 2 divided by 2 is negative 1. So negative 1 comma 4. Next, we have the origin. The origin is going to stay put because 0 divided by 2 is still 0. And next, we have 2 comma negative 2. Divide 2 by 2, we get 1. So that's 1 comma negative 2. And then lastly, 4 comma 0. 4 divided by 2 is 2. And we're going to, so that's 2 comma 0. So now just connect this in that same shape that we just had it. And it'll look something like this, where this is f of 2x. Okay, so one more. So we're going to use f of x, which is the absolute value of x, to graph g of x, which is the absolute value of 2x, and h of x, which is the absolute value of 1/3 x. So I'm going to graph the absolute value of x. That's going to help us graph this. So I'm using the same points that I always do for this one. So we'll get the graph looking like that for the absolute value of x. So taking a look at g of x here, we know it's a horizontal shrink because the value is 2 on the x. It's greater than 1 horizontal shrink. So what that means, we have to divide every x coordinate from the absolute value of x by 2. So it's going to be, I'll start from the left. So for this coordinate all the way over here, for negative 3 comma positive 3, the x coordinate is negative 3. Divide that by 2, and we get negative 3 halves. So negative 3 over 2, which is negative 1.5. The y coordinate stays the same, so it'll be that point. For the next point down here, that was a x coordinate of negative 2. Divide that by 2, we get negative 1. So that'll put us right here. Y coordinate stays the same. Next one, negative 1 comma 1. Divide the x coordinate of negative 1 by 2, we get negative 1/2. Origin stays at the origin, and then it's symmetric, so it'll do the same thing on the other side. So all we did was multiply divide each x coordinate by 2, and the y coordinate stayed the same. So this is going to be g of x, which was absolute value of 2x. Okay, and that's a horizontal shrink. We can see that it got squished in horizontally. Okay, so next for h of x, the absolute value of 1/3 x, we're going to divide the x coordinates by 1/3. So if we're dividing by 1/3, that's actually the same as multiplying by 3. So I'll do it that way because it's obviously a little bit easier. So I'm going to multiply all of the x coordinates from f of x equals the absolute value of x by 3. And the y coordinates are going to stay the same. So starting with this one over here, that's negative 3. So negative 3 times 3 gives us negative 9. So negative 9, the y coordinate stays the same. Next one, there was an x coordinate of negative 2. So that was this one over here. So that's going to be negative 2 times 3 is negative 6. So that's going to be right here. Next one was negative 1 comma 1. So negative 1 was the x coordinate times 3 puts us here. Origin's going to stay at the origin. And then it's symmetric, so it's going to look the same on this side. So it'll look something like this. So that's the absolute value of 1/3 x. It was a horizontal stretch, so you can see that it got moved away from the y-axis. Okay, so now let's start putting these together, and we'll do three examples of these transformations thrown together here. So the key thing to keep in mind here is that the order in which that we apply these transformations actually matters. So I'm just gonna highlight order matters when we're graphing. So what I'm gonna do, what I think is the easiest way to do these, I'm gonna start with the basic function. So I'm gonna identify the basic function, whether it's y equals x squared, y equals the square root of x, y equals the absolute value of x, whatever it is. I'm gonna graph that, and then I'm going to graph the transformations one at a time in the following order until we get the final form of the graph. So the order in which we need to apply these transformations is what I have right here. Horizontal shift first, and then after that apply a vertical or horizontal stretch or shrink, and then apply a reflection, and then apply the vertical shift. So we have to remember the order in which to apply them. If you apply them out of order, it may end up being incorrect. So let's see this example. So g of x is 2 times x plus 3 squared minus 1. So let's identify the basic function first. So we see that there is a squared right up here. So we know the basic function is going to be y equals x squared. So this is going to be the first graph. So I'm going to graph that using the same points I always do. So it looks like that. So next, for graph number 2, the next thing to check was to see if there was a horizontal shift. So there is a horizontal shift, so I'm just going in the correct order of what it said right above this. Not a horizontal shift. So there is a horizontal shift. It's this plus 3 that's on the x, which means we're going to move it to the left 3. So we're going to take this graph and move it to the left 3. So every single coordinate, every single xy point gets moved to the left 3 units. And we end up getting that. So the next thing that we're going to look for based on the order up here is a vertical or horizontal stretch or shrink. There is a vertical stretch because of this 2 that's multiplying out front. So when we have that vertical stretch with the 2, that means we're going to multiply every y value by 2 based on the previous graph. So based on the previous graph up here on the right from the horizontal shift, I'm not going to be able to multiply every y coordinate by 2 because it's going to be off the graph. So I'm going to multiply not the y coordinates of 9 or 4. I'm going to multiply I will do the y coordinate of 4. I just won't do the y coordinates of 9. So I'm going to do these ones right here that I'm highlighting. I'll multiply all of those y coordinates by 2, and I'll leave the x coordinates the same. Can't really fit it all on the same screen. So it's going to end up something like this. Oops. So those y coordinates got multiplied by 2, and we ended up with this. And then lastly is, for the last graph, we have to check for a vertical, let's go back up here to the steps. We check for a reflection next, but there is no reflection here. There's no negative out front or negative multiplying the x, so we skip that. And the last step is the vertical shift. There's a vertical shift right here for that -1. That's going to be a vertical shift down 1 unit. So we're going to take every point from the previous one that we just did and move them all down 1 unit. So we're going to move that down and those 2 down, and we're going to connect these, and we get this is our final answer. This is our g of x, which is 2 times x plus 3 squared minus 1. Okay, so for the next one, we're going to graph f of x, which is negative square root of 2x plus 3 minus 1. So starting off with the basic function for the first one. Since there's a square root here, it's going to be the basic function is y equals the square root of x. And I'm going to use the coordinates that I've previously used for this one. So it's going to be those 4 coordinates. So it looks like this. Okay, so next we're going to check if there is, making sure we're going in the proper order, we're going to check if there is a horizontal shift. There is a horizontal shift. There is that +3. So there's this +3 right here, which means we're moving everything to the left 3 units. So we're going to take every point that we just plotted and move it to the left 3. And we'll end up with this. So this is going to be y equals the square root of x plus 3. Okay, and then for the next thing that we look at, we see if there's a vertical or horizontal stretch or shrink. There is a 2 being multiplied on the x right here. That's going to be a horizontal shrink because it's greater than 1 and it's horizontal, so it's a shrink. So that means for the horizontal shrink, we have to divide every x-coordinate that we just plotted by 2, by that value of 2. So taking a look at the x-coordinates from the one that we just graphed, we have an x-coordinate of -3. If we divide that by 2, we get -3 over 2, so we get -1/2. The y-coordinate stays the same, which was at 0. Then we have an x-coordinate at -2. -2 divided by 2 is -1. So that's going to put us right here. Y-coordinate stays the same. Next, we have a x-coordinate of 1. 1 divided by 2 is 1/2. Y-coordinate stays the same. Lastly, we have a x-coordinate of 6. Divide that by 2, we get 3. And the y-coordinate stays the same, which was also at 3. So we end up getting something like this, where this is y equals the square root of 2x. Was it 2x plus 3? 2x plus 3. Okay, so next we look for a reflection. There is a reflection. There's this negative being multiplied out front, -1. So if it's a negative out front, it's negating the function values, which are the y values, which means we reflect it across the x-axis. So what that means is we take all of the y values from the previous one and we negate them. So the one on the x-axis stays the same. We negate this y value right here. We negate this one down here. And negate this one right here. So we reflect it over the x-axis. And we get this. So now this is negative square root 2x plus 3. And for the last thing here, we have to check if there's a vertical shift. So go back up. There's a vertical shift of -1 at the end. So that means it's going to be a vertical shift down 1. So taking a look at the previous one that we just graphed, we're going to move each one of those points down 1 unit. And we'll end up getting something like this. Okay, and then we connect those. So we get that, and that's going to be our function, which is f of x equals negative square root 2x plus 3 minus 1. So that's our final answer for that one. Okay, so let's do one more. So we have negative x minus 2 cubed. So this time our basic function is one that we didn't really use just yet. Our basic function is the basic cubic function. It's y equals x cubed. So if you want, you can make a table for that. If you make a table for it, it's going to end up being, see, I'll do it up here. Do a little XY table. And I'm going to use those values I wrote down, the integers from -2 to 2. So I'm doing that for a reason, because they're going to fit on the graph. So plugging in -2 into x here, -2 cubed is -8. -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So plotting these points, we're going to get -2 comma -8. -1, -1, 0, 0, 1, 1, and 2, 8. And then connecting these, it's going to look something like this. So we should have known it had this general shape because this is one of the graphs on the first page. Okay, so now we can go in order with our transformations here. So we want to check if there's a horizontal shift first, which there is. There is a horizontal shift because of this -2. So that means we're going to be shifting this to the right 2 units. So we're going to take all of those points and move them to the right 2 units. And we'll get this. And then we just have to connect them again in the same shape. So it'll look something like this. So this is y equals x minus 2 cubed. And next we would check for any vertical or horizontal stretching and shrinking in the function. There's no numbers being multiplied, so we skip it. So next we look for a reflection. There is a reflection because there's the negative on the x. So if there's a negative multiplying the x, that means it's a reflection over the y-axis. So we're going to take all of the points that we just plotted and we're going to reflect them over the y-axis, which is negating the x values. So that's going to look something like this. So these are all the points reflected over the y-axis, and then we connect them. So we get something like that. And lastly, we check for a vertical shift. There is no vertical shift here. There's no plus or minus number completely after the fact. So this is our function, which is h of x equals -x minus 2 cubed. So transformations are nice because this essentially, that's all we can do to functions is add numbers, multiply by numbers, negate numbers, which that's what transformations take into account. So it's a shorter way of graphing instead of having to plot a million points and getting XY points out and plotting those. So make sure definitely you know how to graph those basic functions. You know what they look like on the first page, and you know how to do graphing with transformations. So that is it for 1.6.